let's implement this bubble sort together. It is similar to this one. So let's see how we can implement this algorithm together. So for last, so we are going to have a look at from the last item, and we're going to decrease this value to 1, all right? And the bubble max is going to be in like this. As you saw in this configuration, the current maximum value will bubble to the end, all right? So that is the strategy. So we are going to iterate to the end first, and then we are going to shrink the range of iteration one by one. So in the end, we're going to cover only one item, right? So let's implement this together. So for j in range last minus 1, what we want to do is if aj is larger than aj plus 1, we just swap these two values. So let's say t is aj, and aj is going to be aj plus 1, and aj plus 1 is going to be t. So this is very simple. Okay, so we just compare two items, and if the former value is larger than the later value, then we just swap them. That's all we need to do, right? So this is bubble sort. And one thing we can improve this algorithm is by checking if there is no bubbling, right? So let's say we keep this flipped value, which is false. And if all the values are in order already, then this swapping would not occur, right? So if this swapping occurs, we change this flipped variable to true, like this. And if not flipped, that means every items are in order. So we don't have to continue. So we just return. All right. This is one way to improve this bubble sort. Okay. So we've covered selection sort, insertion sort, bubble sort. And up to this point, do you have any questions? All right. The sorting algorithms we've looked at, selection sort, insertion sort, and bubble sort, are all O(n) square algorithms. And we want to improve these algorithms. So we want better than O(n) square. And that's what we are going to do from this point. And the next sorting algorithm we are going to have a look at is merge sort. And as the name suggests, it is going to divide and merge items. The strategy is like this. We firstly split the list into two halves and sort each sublist recursively. And then, as the name suggests, we are going to merge the two sorted lists. So that is the strategy. And this figure shows, firstly, we divide, and sort each item and merge them. And it is going to be sorted like this. All right, this looks very simple. And let's implement this algorithm together. So from this point, we are going to have a look at merge sort. All right. So for merge sort, we are going to receive a list like this. And as usual, we check whether this list contains more than one element. And if it does not, we just return A like this. And we find the midpoint. And what we're going to do is merge sort A up to midpoint and from mid to end like this. All right. So we are going to merge. What we are going to do is this one looks. We're going to merge sort the left half. And we're going to merge sort the right half like this. And we're going to merge left half and right half like this. All right. So this is very simple. We divide the list into two parts and merge them. And how are we going to merge these two sorted lists? That's what we are going to do here. We are going to receive two lists, A and B. And we're going to make a new list, which is result. While I is smaller than length A, while J is smaller than length B. We're going to iterate through list A and list B. And the value of A is AI. And then value of B is BJ, right? And if VA is smaller than or equal to VB, we are going to append VA. And in this case, we need to increase I like this, and else we're going to append value of B and increase J like this, all right? And at some point, one of these two lists is going to be empty, all right? So what we are going to do is extend AI and BJ like this. However, only one of these will contain some items, all right? One of them is empty. And we return result, all right? So this is the merge algorithm. So merge sort is quite simple. And let's see if this improves the complexity, time complexity, all right? So the time complexity of merge sort, let's check. First, we had n items, and we divide these n items into two parts. So left half and the right half will contain half of the items. And after next iteration, these items will be divided into another left and right half. So it's going to contain n4th items. And in the end, each divisions will contain only one item. And these items are already in order. And we merge them to make the full sorted list. And this n takes complexity of Cn. This is to merge two items. And this takes Cn. And all the items have height of log n. So the total time complexity is going to be n log n. All right. So this is the time complexity of merge sort. And previous sorting algorithms, which were time complexity of O n squared, this one is faster than previous sorting algorithms. And the last sorting algorithm we're going to have a look at is called quicksort. The disadvantage of quick merge sort will be resolved in this quick sort. In merge sort, the divide step was trivial. And the combine step, which was merge, the merge function, is where all the work is done. In quicksort, it is the other way around. The combine step is trivial, and all the work is done in the divide step, right? And the strategy is like this. We select the pivot P from the list L, and we split this L into 3 lists, S, E, and G, where S stores the elements of L which are smaller than X, right? X is the value of pivot P. And E stores the elements of L equal to X. X here is P. And G stores the elements of L which are greater than X. And after this, we just concatenate S, E, G. And that's all we need to do. And this is the figure. We first find the pivot like this with pivot here. And if this value is smaller than pivot, and this value is smaller than pivot, and this one is greater than pivot, we just replace them. Actually, this one is in place operation. And this strategy is for recursive version. Let's implement this first and then have a look at this in place operation next, right? So what we are going to implement is quicksort. And we're going to implement the recursive version first. If length is smaller than 1, as usual, we just return A. And we find a pivot. We just say the pivot is the middle value. All right. And as I told you, we are going to create 3 lists like this. Small, equal, and large. And for each item in A, if X is smaller than pivot, we're going to append this value to small list. And if this value equals to pivot, like this, and we returned quicksort the small, like this, all right? So this is very simple to implement. We just find smaller values and equal values and larger values. And we just concatenate the quick sorted version of smaller list and quick sorted version of larger list and concatenate them. So this is recursive implementation, and this is not in place operation, all right? So how can you make this in place? One way to make this in place is this figure. So we compare all the values with pivot, and we just exchange some values that are smaller than pivot to the left, and the values larger than pivot on the right. So all the values smaller than pivot will be located on the left half, and all the values larger than pivot will be located on the right. So that's why we find from the left, search from the left and search from the right, and find some values that are smaller than pivot or larger than pivot and swap them. In such way, we can locate all the items smaller than pivot on the left and all the items larger than pivot on the right. All right. And let's implement this in place version together. So we are going to implement this in place algorithm together. If LO is smaller than HI, what we want to do is we find pivot index like this. We partition, we're going to make another function called partition like this. And we are going to quick sort the left half and the right half like this. And how are we going to partition? This one is quite tricky, and let's implement this together. What we are going to do is exactly what this figure is illustrating. We first find the pivot and put all the values on the left or right, right? Let's do this. We're going to select the value in the middle as our pivot, right? And the value of this position is going to be our pivot. And we place this pivot at the end of this list, right? And like this, okay? So what we are going to do is from the left side and from the right side, we're going to search the items that are smaller than pivot. And while I is smaller than j, we're going to increment I one by one. And while AI is smaller than pivot, we're going to increase I. All right. So after this while loop, we find the value that is larger than pivot. And we're going to put that value to the right side. All right. And we search from the right side. So what we are going to is decrease J. And while AJ is larger than pivot and J is larger than LO, low point, we're going to decrement J like this. So after this while loop, we find an AJ, which is smaller than pivot. And what we are going to do is, if I is small, we are going to swap AI and AJ like this, all right? So we first say AI is like this, and we put AJ into AI like this, and we are going to put AJ into T, all right? So that's all we need to do. Sorry, my monitor is out of power. So this is basically how we solve this problem. And we return the position of pivot like this. So that's all we need to do. All right. So this is how we can implement quicksort. So we have implemented this behavior. Okay. And let's analyze our quicksort. In the worst case, the quicksort is the complexity of n squared. It happens when the partition between one element and n minus one elements. In this case, the time complexity is Tn is going to be O1 plus Tn minus 1. And if it happens again and again, that means we are doing On squared. And the best case is time complexity of On log n. This happens when we partition the items with exact two equal parts, half elements on the left and half elements on the right, because the time complexity is going to be look like this. Tn is going to be 2 times T, half of items on the left and half of items on the right. And to merge them, for swapping items, it takes On. And when we solve this recurrence equation, it's going to be n log n. And this worst case does not happen frequently. And to get this best case more frequently, we usually choose a pivot value randomly. And in our implementation, we chose our pivot that is located in the middle. However, we can change that implementation so that we could choose pivot randomly. And there are some fun facts about quicksort. Quicksort was chosen as one of the 10 most important and influential algorithms of the 20th century. Among the 10, quicksort was the simplest. And another thing is, the inventor of quicksort received the ACM Turing Award, which is like Nobel Prize in computer science, for his work on programming languages, not for quicksort.